Tritium is a radioactive isotope of hydrogen. The nucleus of tritium contains 1 proton and 2 neutrons, whereas the nucleus of protium contains 1 proton and no neutrons. Naturally occurring tritium is extremely rare on Earth, where trace amounts are formed by the interaction of the atmosphere with cosmic rays. The name of this isotope is formed from the Greek word tritos meaning third. Decay. While tritium has several different experimentally determined values of its half-life, the National Institute of Standards and Technology lists 4,500 or plus or minus 8 days. It decays into helium-3 by beta decayers in this nuclear equation. And it releases 18.6 keV of energy in the process. The electron's kinetic energy varies, with an average of 5.7 keV, while the remaining energy is carried off by the nearly undetectable electron antineutrino. Beta particles from tritium can penetrate only about 6.0 ohm of air, and they are incapable of passing through the dead outermost layer of human skin. The unusually low energy released in the tritium beta decay makes the decay appropriate for absolute neutrino mass measurements in the laboratory. The low energy of tritium's radiation makes it difficult to detect tritium-labeled compounds except by using liquid scintillation counting. Production. Lithium. Tritium is produced in nuclear reactors by neutron activation of lithium-6. This is possible with neutrons of any energy, and is an exothermic reaction yielding 4.8 MeV. In comparison, the fusion of deuterium with tritium releases about 17.6 MeV of energy. High-energy neutrons can also produce tritium from lithium-7 in an endothermic reaction, consuming 2.466 MeV. This was discovered when the 1954 Castle Bravo nuclear test produced an unexpectedly high yield. High-energy neutrons irradiating boron-10 will also occasionally produce tritium. A more common result of boron-10 neutron capture is 7 Li and a single alpha particle. The reactions requiring high neutron energies are not attractive production methods. Deuterium. Tritium is also produced in heavy water moderated reactors whenever a deuterium nucleus captures a neutron. This reaction has a quite small absorption cross-section, making heavy water a good neutron moderator, and relatively little tritium is produced. Even so, cleaning tritium from the moderator may be desirable after several years to reduce the risk of its escaping to the environment. The Ontario Power Generation's tritium removal facility processes up to 2,500 tons of heavy water a year, and it separates out about 2.5 kg of tritium, making it available for other uses. Deuterium's absorption cross-section for thermal neutrons is about 0.52 millibarns, whereas that of oxygen-16, 80, is about 0.19 millibarns and that of oxygen-17, 80, is about 240 millibarns. 80 makes up about 0.038% of all naturally occurring oxygen, hence oxygen has an overall absorption cross-section of about 0.28 millibarns. Therefore, in heavy water made with natural oxygen, 21% of neutron captures are by oxygen nuclei, a proportion that may rise further since the percentage of 80 increases from neutron captures by 80. This reaction creates radioactive carbon-14, 6C, a dangerous byproduct, 80 plus Na14, 6C plus 4, 2He, 80 also splits when bombarded by the alpha particles emitted by decaying uranium, producing 6C, by the equation, 80 plus 4, 2He 6C plus assorted smaller products. Fission. Tritium is an uncommon product of the nuclear fission of uranium-235, plutonium-239, and uranium-233, with a production of about 1 atom per each 10,000 fissions. The release or recovery of tritium needs to be considered in the operation of nuclear reactors, especially in the reprocessing of nuclear fuels and in the storage of spent nuclear fuel. The production of tritium is not a goal, but rather a side effect. Fukushima Daiichi. In January 2014 it was made public that a total of 875 terabecquerels of tritium are on the site of Fukushima Daiichi, and the amount of tritium contained in the contaminated water is increasing by approximately 230 terabecquerel per year. According to a report by TÜV, tritium could be separated theoretically, but there is no practical separation technology on an industrial scale. Helium-3 and tritium. Tritium's decay product, helium-3, has a very large cross-section for reacting with thermal neutrons, expelling a proton, hence it is rapidly converted back to tritium in nuclear reactors. 3, 2 He plus Na1, 1 hour plus 3, 1 hour, cosmic rays. Tritium occurs naturally due to cosmic rays interacting with atmospheric gases. In the most important reaction for natural production, a fast neutron interacts with atmospheric nitrogen. The global equilibrium inventory of tritium is approximately constant due to a fixed production rate and losses proportional to the inventory. Production history. According to the Institute for Energy and Environmental Research report in 1996 about the U.S. Department of Energy, only 225 kg of tritium has been produced in the United States since 1955. Since it continually decays into helium-3, the total amount remaining was about 75 kg at the time of the report. Tritium for American nuclear weapons was produced in special heavy water reactors at the Savannah River site until their close downs in 1988. With the Strategic Arms Reduction Treaty after the end of the Cold War, the existing supplies were sufficient for the new, smaller number of nuclear weapons for some time. The production of tritium was resumed with irradiation of rods containing lithium, at the reactors of the commercial Wattsbauer nuclear generating station in 2003–2005, followed by extraction of tritium from the rods at the new tritium extraction facility at the Savannah River site beginning in November 2006. Tritium leakage from the TPBARs during reactor operations limits the number that can be used in any reactor without exceeding the maximum allowed tritium levels in the coolant. Properties. Tritium has an atomic mass of 3.0160492 U. It is a gas at standard temperature and pressure. It combines with oxygen to form a liquid called tritiated water, T2O. Tritium's specific activity is 9,650 curies per gram. Tritium figures prominently in studies of nuclear fusion because of its favorable reaction cross-section and the large amount of energy produced through its reaction with deuterium. All atomic nuclei, being composed of protons and neutrons, repel one another because of their positive charge. However, if the atoms have a high enough temperature and pressure, then their random motions can overcome such electrical repulsion, and they can come close enough for the strong nuclear force to take effect, fusing them into heavier atoms. The tritium nucleus, containing 1 proton and 2 neutrons, has the same charge as the nucleus of ordinary hydrogen, and it experiences the same electrostatic repulsive force when brought close to another atomic nucleus. However, the neutrons in the tritium nucleus increase the attractive strong nuclear force when brought close enough to another atomic nucleus. As a result, tritium can more easily fuse with other light atoms, compared with the ability of ordinary hydrogen to do so. The same is true, albeit to a lesser extent, of deuterium. This is why brown dwarfs cannot utilize ordinary hydrogen, but they do fuse the small minority of deuterium nuclei. Like hydrogen, tritium is difficult to confine. Rubber, plastic, and some kinds of steel are all somewhat permeable. This has raised concerns that if tritium were used in large quantities, in particular for fusion reactors, it may contribute to radioactive contamination, although its short half-life should prevent significant long-term accumulation in the atmosphere. The high levels of atmospheric nuclear weapons testing that took place prior to the enactment of the Partial Test Ban Treaty proved to be unexpectedly useful to oceanographers. The high levels of tritium oxide introduced into upper layers of the oceans have been used in the years since then to measure the rate of mixing of the upper layers of the oceans with their lower levels. Health risks. Tritium is an isotope of hydrogen, which allows it to readily bind to hydroxyl radicals, forming tritiated water, and to carbon atoms. Since tritium is a low-energy beta emitter, it is not dangerous externally, but it is a radiation hazard when inhaled, ingested via food or water, or absorbed through the skin. H2O has a short biological half-life in the human body of 7 to 14 days, which both reduces the total effects of single-incident ingestion and precludes long-term bioaccumulation of H2O from the environment. Biological half-life of tritiated water in human body, which is a measure of body water turnover, varies with season. Studies on biological half-life of occupational radiation workers for free water tritium in the coastal region of Karnataka, India show that the biological half-life in winter season is twice that of the summer season. According to the US EPA, a recently documented source of tritium in the environment is self-illuminating exit signs that have been illegally disposed of in municipal landfills. Water, which seeps through the landfill, is contaminated with tritium from broken signs and can pass into waterways, carrying the tritium with it. Tritium has leaked from 48 of 65 nuclear sites in the U.S. In one case it was detected in groundwater at levels exceeding the United States Environmental Protection Agency drinking water standards by up to 375 times. The U.S. Nuclear Regulatory Commission states that in normal operation in 2003, 56 pressurized water reactors released 40,600 curies of tritium and 24 boiling water reactors released 665 curies, in liquid effluents. Regulatory limits. The legal limits for tritium in drinking water vary from country to country. Some figures are given below. Tritium drinking water limits in various countries. World Health Organization, 10,000 becquerel per liter. Canada, 7,000 becquerel per liter. United States, 740 becquerel per liter or 20,000 pCIL. European Union, investigative limit of 100 becquerels per liter. The American limit is calculated to yield a dose of 4.0 mg per year. This is about 1.3% of the natural background radiation. Use: self-powered lighting. The emitted electrons from the radioactive decay of small amounts of tritium cause phosphors to glow so as to make self-powered lighting devices called beacon lights, which are now used in firearm night sights, watches, exit signs, map lights, knives and a variety of other devices. This takes the place of radium, which can cause bone cancer and has been banned in most countries for decades. Commercial demand for tritium is 400 grams per year and the cost is approximately $30,000 per gram. Nuclear weapons. Tritium is an important component in nuclear weapons. It is used to enhance the efficiency and yield of fission bombs and the fission stages of hydrogen bombs in a process known as boosting, as well as in external neutron initiators for such weapons. Neutron initiator, actuated by an ultra-fast switch like a triton, a small particle accelerator drives ions of tritium and deuterium to energies above the 15 kV or so needed for deuterium-tritium fusion and directs them into a metal target where the tritium and deuterium are adsorbed as hydrides. High-energy fusion neutrons from the resulting fusion radiate in all directions. Some of these strike plutonium or uranium nuclei in the primaries pit, initiating nuclear chain reaction. The quantity of neutrons produced is large in absolute numbers, allowing the pit to quickly achieve neutron levels that would otherwise need many more generations of chain reaction, though still small compared to the total number of nuclei in the pit. Boosting. Before detonation, a few grams of tritium-deuterium gas are injected into the hollow pit of fissile plutonium or uranium. The early stages of the fission chain reaction supply enough heat and compression to start deuterium-tritium fusion, then both fission and fusion proceed in parallel, the fission assisting the fusion by continuing heating and compression, and the fusion assisting the fission with highly energetic neutrons. As the fission fuel depletes and also explodes outward, it falls below the density needed to stay critical by itself. But the fusion neutrons make the fission process progress faster and continue longer than it would without boosting. Increased yield comes overwhelmingly from the increase in fission. The energy released by the fusion itself is much smaller because the amount of fusion fuel is so much smaller. The effects of boosting include increased yield, the possibility of variable yield by varying the amount of fusion fuel, allowing the bomb to require a smaller amount of the very expensive fissile material and also eliminating the risk of pre-detonation by nearby nuclear explosions, not so stringent requirements on the implosion setup, allowing for a smaller and lighter amount of high explosives to be used, the tritium in a warhead is continually undergoing radioactive decay, hence becoming unavailable for fusion. Furthermore, its decay product, helium-3, absorbs neutrons if exposed to the ones emitted by nuclear fission. This potentially offsets or reverses the intended effect of the tritium, which was to generate many free neutrons, if too much helium-3 has accumulated from the decay of tritium. Therefore, it is necessary to replenish tritium in boosted bombs periodically. The estimated quantity needed is 4 grams per warhead. To maintain constant levels of tritium, about 0.20 grams per warhead per year must be supplied to the bomb. 1 mole of deuterium-tritium gas would contain about 3.0 grams of tritium and 2.0 grams of deuterium. In comparison, the 20 moles of plutonium in a nuclear bomb consists of about 4.5 kilograms of plutonium-239. Tritium in hydrogen bomb secondaries. Since tritium undergoes radioactive decay, and it is also difficult to confine physically, the much larger secondary charge of heavy hydrogen isotopes needed in a true hydrogen bomb uses solid lithium deuteride as its source of deuterium and tritium, where the lithium is all in the form of the lithium-6 isotope. During the detonation of the primary fission bomb stage, excess neutrons released by the chain reaction split lithium-6 into tritium plus helium-4. In the extreme heat and pressure of the explosion, some of the tritium is then forced into fusion with deuterium, and that reaction releases even more neutrons. Since this fusion process requires an extremely high temperature for ignition, and it produces fewer and less energetic neutrons, only fission, deuterium-tritium fusion, and 7,3 splitting are net neutron producers. Lithium deuteride is not used in boosted bombs, but rather, for multistage hydrogen bombs. Controlled nuclear fusion. Tritium is an important fuel for controlled nuclear fusion in both magnetic confinement and inertial confinement fusion reactor designs. The experimental fusion reactor ITER and the National Ignition Facility will use deuterium-tritium fuel. The deuterium-tritium reaction is favorable since it has the largest fusion cross-section and it reaches this maximum cross-section at the lowest energy of any potential fusion fuel. The Tritium Systems Test Assembly was a facility at the Los Alamos National Laboratory dedicated to the development and demonstration of technologies required for fusion-relevant deuterium-tritium processing. Analytical chemistry. Tritium is sometimes used as a radiolabel. It has the advantage that hydrogen appears in almost all organic chemicals, making it easy to find a place to put tritium on the molecule under investigation. It has the disadvantage of producing a comparatively weak signal. Used as an oceanic transient tracer, aside from chlorofluorocarbons, tritium can act as a transient tracer and has the ability to outline the biological, chemical, and physical paths throughout the world oceans because of its evolving distribution. Tritium has thus been used as a tool to examine ocean circulation and ventilation and, for such purposes, is usually measured in tritium units where 1 Tu is defined as the ratio of 1 tritium atom to 1018 hydrogen atoms. As noted earlier, nuclear weapons testing, primarily in the high-latitude regions of the Northern Hemisphere, throughout the late 1950s and early 1960s introduced large amounts of tritium into the atmosphere, especially the stratosphere. Before these nuclear tests, there were only about 3 to 4 kilograms of tritium on the Earth's surface. But these amounts rose by 2 or 3 orders of magnitude during the post-test period. North Atlantic Ocean. While in the stratosphere, the tritium interacted with and oxidized to water molecules and was present in much of the rapidly produced rainfall, making tritium a prognostic tool for studying the evolution and structure of the hydrologic cycle as well as the ventilation and formation of water masses in the North Atlantic Ocean. Bomb tritium data were used from the transient tracers in the Ocean program in order to quantify the replenishment and overturning rates for deep water located in the North Atlantic. Most of the bomb tritiated water throughout the atmosphere can enter the ocean through the following processes: A. Precipitation, B. Vapor exchange, and C. River runoff. These processes make H2O a great tracer for timescales up to a few decades. Using the data from these processes for 1981, the 1Tu isosurface lies between 500 and 1,000 meters deep in the subtropical regions and then extends to 1,500 to 2,000 meters south of the Gulf Stream due to recirculation and ventilation in the upper portion of the Atlantic Ocean. To the north, the isosurface deepens and reaches the floor of the abyssal plain, which is directly related to the ventilation of the ocean floor over 10 to 20-year time scales. Also evident in the Atlantic Ocean is the tritium profile near Bermuda between the late 1960s and late 1980s. There is a downward propagation of the tritium maximum from the surface to 400 meters, which corresponds to a deepening rate of approximately 18 meters per year. There are also tritium increases at 1,500 meters depth in the late 1970s and 2,500 meters in the middle of the 1980s, both of which correspond to cooling events in the deep water and associated deep water ventilation. From a study in 1991, the tritium profile was used as a tool for studying the mixing and spreading of newly formed North Atlantic deep water, corresponding to tritium increases to 40U. This NADW tends to spill over sills that divide the Norwegian Sea from the North Atlantic Ocean and then flows to the west and equatorward in deep boundary currents. This process was explained via the large-scale tritium distribution in the deep North Atlantic between 1981 and 1983. The subpolar gyre tends to be freshened by the NADW and is directly related to the high tritium values. Also evident was the decrease in tritium in the deep western boundary current by a factor of 10 from the Labrador Sea to the tropics, which is indicative of loss to ocean interior due to turbulent mixing and recirculation. Pacific and Indian Oceans. In a 1998 study, tritium concentrations in surface seawater and atmospheric water vapor were sampled at the following locations: the Sular Sea, the Fremantle Bay, the Bay of Bengal, the Penang Bay, and the Strait of Malacca. Results indicated that the tritium concentration in surface seawater was highest at the Fremantle Bay, which could be accredited to the mixing of runoff of fresh water from nearby lands due to large amounts found in coastal waters. Typically, lower concentrations were found between 35 and 45 degrees south latitude and near the equator. Results also indicated that tritium has decreased over the years due to the physical decay of bond tritium in the Indian Ocean. As for water vapor, the tritium concentration was approximately 1 order of magnitude greater than surface seawater concentrations. Therefore, the water vapor tritium is not affected by the surface seawater concentration. Thus, the high tritium concentrations in the vapor were concluded to be a direct consequence of the downward movement of natural tritium from the stratosphere to the troposphere. In the North Pacific Ocean, the tritium spread in 3 dimensions. There were subsurface maxima in the middle and low latitude regions, which is indicative of lateral mixing and diffusion processes along lines of constant potential density in the upper ocean. Some of these maxima even correlate well with salinity extrema. In order to obtain the structure for ocean circulation, the tritium concentrations were mapped on 3 surfaces of constant potential density. Results indicated that the tritium was well mixed on the 26.81 isopucanol in the subarctic cyclonic gyre, and there appeared to be a slow exchange of tritium between this gyre and the anticyclonic gyre to the south. Also, the tritium on the 23.90 and 26.02 surfaces appeared to be exchanged at a slower rate between the central gyre of the North Pacific and the equatorial regions. The depth penetration of bond tritium can be separated into 3 distinct layers. Layer 1 is the shallowest layer and includes the deepest, ventilated layer in winter. It has received tritium via radioactive fallout and lost some due to advection and/or vertical diffusion, and contains approximately 28% of the total amount of tritium. Layer 2 is below the first layer but above the 26.81 isopucanol and is no longer part of the mixed layer. Its 2 sources are diffusion downward from the mixed layer and lateral expansions outcropping strata. It contains about 58% of the total tritium. Layer 3 is representative of waters that are deeper than the outcrop isopucanol and can only receive tritium via vertical diffusion. It contains the remaining 14% of the total tritium. Mississippi River system. The impacts of the nuclear fallout were even felt in the United States throughout the Mississippi River system. Tritium concentrations can be used to understand the residence times of continental hydrologic systems, which include surface waters such as lakes, streams, and rivers. Studying these systems can also provide societies and municipals with information for agricultural purposes and overall river water quality. In a 2004 study, several rivers were taken into account during the examination of tritium concentrations throughout the Mississippi River Basin, Ohio River, Missouri River, and Arkansas River. The largest tritium concentrations were found in 1963 at all the sampled locations throughout these rivers and correlate well with the peak concentrations in precipitation due to the nuclear bomb tests in 1962. The overall highest concentrations occurred in the Missouri River and were greater than 1,200 TU, while the lowest concentrations were found in the Arkansas River. Several processes can be identified using the tritium data from the rivers: direct runoff and outflow of water from groundwater reservoirs. Using these processes, it becomes possible to model the response of the river basins to the transient tritium tracer. Two of the most common models are the following: piston flow approach, tritium signal appears immediately, and well-mixed reservoir approach, outflow concentration depends upon the residence time of the basin water. Unfortunately, both models fail to reproduce the tritium in river waters. Thus, a two-member mixing model was developed that consists of two components, a prompt flow component and a component where waters reside in the basin for longer than 1 year. Therefore, the basin tritium concentration becomes a function of the residence times within the basin, sinks or sources of tritium, and the input function. For the Ohio River, the tritium data indicated that about 40% of the flow was composed of precipitation with residence times of less than 1 year, and older waters consisted of residence times of about 10 years. Thus, the short residence times corresponded to the prompt flow component of the two-member mixing model. As for the Missouri River, results indicated that residence times were approximately 4 years, with the prompt flow component being around 10%. As for the mass flux of tritium through the main stem of the Mississippi River into the Gulf of Mexico, data indicated that approximately 780 grams of tritium has flowed out of the river and into the Gulf between 1961 and 1997. And current fluxes through the Mississippi River are about 1 to 2 grams per year, as opposed to the pre-bomb period fluxes of roughly 0.4 grams per year. History: tritium was first produced in 1934 from deuterium, another isotope of hydrogen, by Ernest Rutherford, working with Mark Oliphant and Paul Hartek. Rutherford was unable to isolate the tritium, a job that was left to Luis Alvarez and Robert Cornog, who correctly deduced that the substance was radioactive. Willard F. Libby discovered that tritium could be used for dating water, and therefore wine. See also, hypertriton, luminux, deuterium. References. Bibliography: B. M. Andreev, E. P. Magomedbekov, G. H. Sicking, Interaction of Hydrogen Isotopes with Transition Metals and Intermetallic Compounds, Springer Tracts in Modern Physics, Springer, Berlin. External links: annotated bibliography for tritium from the ALSOS Digital Library, NLM Hazardous Substances Data Bank, Tritium, Radioactive, Nuclear Data Evaluation Lab, Review of Risks from Tritium. Report of the Independent Advisory Group on Ionizing Radiation, Health Protection Agency. November 2007. RCE Fora, Tritium on Ice, The Dangerous New Alliance of Nuclear Weapons and Nuclear Power, by Kenneth D. Bergeron, Tritium Production and Recovery in the United States and FY 2011, Tritium Removal Mass Transfer Coefficient.